Okay, now consider the temperature effect on the separation. Okay? Temperature could be used as a variable. Okay, look at this square. Okay, and you see A, B, C, and D. Okay, and temperature can affect relative rotation. The general principle is that the high temperature gives you the fast um, illusion, okay, the fast separation, but your separation what may not be good, okay. So this square can you help which temperature and which solvent composition is optimum, okay. Let's take a look here. The A indicates a high percent B. B means organic solvent. Okay? Highest organic solvent means the lower aqueous vapor, the percentage. Okay, and high uh, the B and low T. And if you can increase the temperature, then it means a high percent B and high temperature. Okay, and if you increase B at the same low temperature, and like that. Okay, and here you have to choose isocratic method development for HPLC using solvent composition percent B and temperature T as independent variables. Okay, so you can treat these two variables as independent variables. Okay? Percent B and T are each varied between selected low and high values. Okay, so since you can independently change, the percent, B percent, and the temperature. Okay, so and then you look at the chromatograms. Okay? And then you choose which condition is good. Okay, or you can maybe choose in between, all right, for the best separation. Okay? So your decision is based on the appearance of chromatograms, okay, resulting from these conditions. But there is a one thing you have to be careful, which is that for elevated uh, temperature operation, pH should be below 6 to retard dissociation of silica stationary phase. Okay, at high temperature and the solution pH is greater than 6, then may degrade. Okay, uh, the silica stationary phase, right? And I think the most important part in HPLC is to is which stationary phase to choose. Okay, mostly the octadecyl bonded silica phase is the most commonly used stationary phase. Yeah? This is actually very good. The bonded phase, okay, octadecyl group is very good, but however, it cannot achieve all separations. In that case, you have to decide which stationary phase to choose. Here is some guidelines. Okay? First, change solvent strength by varying uh, composition. Okay, we we've already considered how to choose solvent. Okay, one solvent, the or two or three solvents with aqueous buffer, and also you can change the temperature and change the pH, and you otherwise if this are not working well, and you use different solvent. Okay, and then you can choose a different kinds of stationary phase. Okay, so the this table tells you something some important information about selecting the bonded stationary phase, okay, for HPLC. Okay, here, if the bonded phase is octadecyl or octyl, or this one is butyl group, that gives you non-polar, okay, properties to the stationary phase. Okay, and so retention mechanism is van der Waals interaction. Okay, van der Waals interaction, because they are all non-polar. Okay, interaction between these bonded groups and your solute may be the van der Waals interactions. Okay, van der Waals interactions actually is everywhere. Okay, no matter what the molecular structure is. Okay, and so this bonded phase is good for for many molecules. Here is comments. C8, octyl, the bonded phase does not retain hydrophobic compound as strongly as this one, the octadecyl group. Yeah, this is true because van der Waals interactions in octadecyl group is much stronger than the other on the bonded phase, because this group octadecyl is a very long chain. So when carbon number of carbons is many, van der Waals interactions will increase. Okay, and you may choose penyl bonded phase. Okay, this is also good for non-polar compounds. Yeah, because this property is also non-polar. Penyl. Penyl group is kind of non-polar. Okay, but not as non-polar as this one, but still non-polar. So retention mechanism is also hydrophobic interaction, and here pi-pi interaction. Why? The phenyl, the phenyl group. Okay, the phenol, right? Phenol is the what? The benzene ring, and hydroxyl group is attached. Okay, hydroxyl group substitute one of the hydrogen atom. So there is a pi-pi interaction. The phenyl group also 6 pi electrons. Okay, so when the solute, okay, when solute molecules have pi electrons, there are pi-pi interactions between the solute molecules and phenyl groups. Okay, and also hydrophobic interaction is there, and the cyano group bonded phase, the polarity is intermediate. Okay, cyano group CN, right? Because N nitrogen is has a higher electronegativity, so polarity is intermediate. So the retention mechanism is hydrophobic, and dipole interaction, and pi-pi interaction. Okay, dipole because of the electronegativity, the difference. The cyano group has a dipole moment. Right? So if a solute has a dipoles, and then it can be well separated by this column. This one resolves polar organic compounds by reversed phase or normal phase chromatography. Okay, that's this column is good for polar organic compound. Right? And amino acid, yeah, amino group. I'm sorry, this one NH2. This is the more polar than the cyano group. Okay, and it takes the charge. Okay, this amine group takes a positive charge by accepting the proton, especially when in the pH, in a neutral pH. Okay, neutral or acidic pH. So this amino group bonded phase is good for for the polar molecules. Okay, polar organic compounds. Yeah? And inorganic ions and interact with aldehyde and ketones. Aldehyde and ketones also have dipole moment. Mm. It's a normal phase where ion exchange separation is possible. Okay, so retention mechanism is dipole-dipole and hydrogen bonding, because it contains a nitrogen atom here. And finally, bare silica. Yeah, bare silica is very polar. Okay, and the retention mechanism is hydrogen bonding. This the separation is done uh, by normal phase separations. Actually, normal phase means that the stationary phase is polar, right? And inverse uh, reversed stationary phase means that stationary phase is nonpolar. Okay, so this table gives you a good guideline for choosing a stationary phase. Okay, here is an example, right? The the question is suggest an approach to resolve the following compound in a short time. Now you are, let's assume you are asked to separate all these compounds, yeah, rapidly, yeah, and very efficiently, yeah, with high resolution. Okay, and these six compounds are all similar. Okay, they have this part. Okay, one this what this benzene ring and two fused ring here. Okay, so this structure is called flavonoid. Okay, flavonoid. The differences may be in this part and this part, and here is a double bond, and this one single bond. Okay, and here is the hydroxy group, but no hydroxy group. Okay, and this one, this is what this glucose. Okay, glucose group here. Okay, so all the with the same basic structure, and then it has many kinds of this kind of compounds. Yeah, they are called flavonoid. Okay, and then each of them has its own name. This is a lutein. Yeah, lutein is very important for our health. Okay, to make our eyes healthy, you may want to take lutein, and catechin and myricetin and quercetin, apigenin and naringenin. Have some experience of just quercetin. Yeah? I've developed a sensor detecting quercetin out of other flavonoids. Anyway, the question is how to, this is flavonoids, how to separate all these very well. Okay, so how to choose is stationary phase. Okay, that but the close inspection of these structures reveal that all lutein, catechin, myricetin, and quercetin, they are structures are rather different. Okay, rather different. But problem is that apigenin and naringenin, because only difference is there here, this part. That apigenin has double bond here, and the naringenin, this part is a single bond. Okay, so other parts are exactly the same. Mm. So question is actually how to separate these compounds. Okay, here is a solution. So compounds have similar structures. Hard to separate. Okay, especially compound 5 and 6 are almost similar, differing by just one bond. Okay, so we have to look up the table. 24-5 suggests that stationary phase with phenyl and cyano groups which retain analyzed by pi-pi interactions might be good for distinguishing 5 and 6. What does it mean that? Look at that. Although the structures are quite similar, look at that, this part. Yeah? Apigenin. Yeah? Here is a double bond, single, double, okay? Yeah? Here, double, single, double, single, double, single. Yeah? Okay? So that kind of structure is called pi structure. Okay? So electrons here are delocalized in this middle ring. Okay, why? Double single, double single, double single, double single, double single. Yeah, like that. Yeah? So when you find double bond and single bond are uh, alternatively there, and then that is the pi electrons are pi electrons. Okay, so pi interactions will be there. Okay, but here Naringani in this part, since there is no double bond, of course this part, this one is double single, double single, double single. Yeah, this part has pi electrons, and also this one. But here it doesn't have the electrons on this carbon and carbon. No, that electron, those electrons are not pi electrons. So pi system in this case is broken inside in this middle ring. So to separate this one, and then you have to have stationary phase with pi interactions. That which one is that? Pi interaction. Maybe this one, phenyl group here, or cyano bonded phase. Okay? And look at that. Yeah. Now we have two chromatograms A and B. Definitely, A gives better resolution, especially for compound 5 and 6. Okay, this one is done by this good separation is done by phenyl silica column here. Phenyl silica, okay, phenyl bonded to silica. This stationary phase has a pi. You see, the pi, the interaction is working there. So this is good for separating compound 5 and 6. In the meantime, this one is obtained with octadecyl silica column. Octadecyl here, there is no pi interactions, all right? You understand? But other compounds, 1, 2, 3, 4, yeah? These compounds are well separated with this octadecyl bonded column, okay? Here. Since this one, 5 compound, it has pi interaction, pi bond, pi electrons, so it is well separated, okay? Then compound 6 is comes out of after the compound 5,